today's hullabaloo, we're going to be talking about modules. So consider this our third footnote ever since we completed the course. So note that every time we finish the course, there will be footnotes or some like sub-lectures. Maybe even some of these sub-lectures may be longer than the original lectures, but lectures nonetheless. And these lectures are sort of, as I said, footnotes. They're sort of additional addendums or shit like that we. I'm not supposed to swear. Just some additional things that we want to consider or want to add to the theory. All right. So, if I can just find it. Module. So, we already considered some basic mathematical structures, such as the magma, simple magma, and we characterize that in our theory as a simple field of femboys, maybe. So, say the universal underlying set of femboys is equipped with some operation, say star, such that any F1 star F2 is inside F. That's what it means for it to be some magma. That's what it means for it to be a magma, or the most basic mathematical structure. Closure, it has closure, and things like that. So now, what we want to consider is the module. So what is a module? If I can fucking find it. If I can just find my notes here. It's very hard to remember these things when you study multiple subjects. Right, modules. So, what is a module? So, in abstract algebra, or in pure mathematics, a module is a mathematical structure. So it's just like a group, or something like it's something like I suppose a magma or a group or a monoid or something like that. So formally speaking, a module is a generalization of a vector space. So you guys know about vector spaces, sets containing vectors. Something like this. That's a vector space. So what is the generalization of this thing? Because we know that regular sets, like say A, can be generalized into a sort of element of a category, C. So we can say that A is an element of a category. And then we have certain transforms or morphisms or functions that make A into some other set B. And then that B is also an element of the category. And so let's say that this is some bar phi or bar phi, and then phi is part of the construction of our category. So that's a generalization of sets in general, or maybe mathematical structures in general. So what is the generalization or the higher form wherein we can say a vector space is part of? Well, that, my students, is called a module. So V will be part of something called a module. And these guys have so much applications, especially in probability theory and some mathematical physics. In fact, Ralu, my friend in Discord that I keep talking about, discussed me, or when I asked him what's the next thing I should consider in my theory, he told me modules. And maybe after that we could consider tangent bundles, and then perhaps try to, like what he did, construct a density space and find its Hamiltonian. So, okay, so enough jibber jabber. Let's discuss what a module is. So, we know that a field of scalars is a ring. So we know about rings. It's also a type of mathematical structure that has closeness and it has some additional properties, but it's not necessarily a group. So if a group could be any mathematical structure, a ring is something like a group, but only containing scalars. So only one-dimensional quantities or quantities that are described via some real axis, something like that, or maybe one part of a complex axis. So probably the imaginary complex part of an axis would define, or equipped with some operation would probably define some kind of ring. Or perhaps the set of all matrices, or maybe GL, the general linear group, or some subset of it can be called a ring, I suppose. So let R be a ring, and I its multiplicative entity. So first let's define what a ring is. So a ring. So a ring are equipped, is a set equipped with the addition with two binary operators which is some plus that maps an R, or rather R, or just R, regular, not that kind of R, sorry, that maps R cross R onto R. Let's make that arrow more visible. So this first operation and our second operation, which is our dot, that also sends R cross R onto R. That's what's called a binary operator because it only takes in two outputs. A multilinear operator, such as, well, an infinite amount of additions like 1 plus 2 plus 3. This is not part of this operation because this will take in three inputs, 1, 2, and 3, and it would spit out some output, which is 6. So this would be some trinary operator. So this would R cross R cross R. And they give us an output inside R. So that's the difference between a multilinear or multinary, something, or polynary, or trinary operator with a binary operator. We say binary operator, that means we're taking in two inputs and then having one output. So it's only 1 plus 2, 3 plus 2, 5 plus 4, 1 half plus 3 halves, something like that. Okay, so now R, so let's call our ring R equals, well, our underlying set R, let's call our underlying set R bar with these two operations satisfies the ring axioms. So the ring axioms are it's simply, we have three main axioms for a ring. The first one is that R is an abelian group under addition. So the construction R equipped with the addition operation, our first binary operator, is an abelian group. So for any two inputs here, swapping the inputs would give the same thing. So like how you learned in basic algebra, A plus B is equal to B plus A. So that's what we're saying here. Abelian group. The second ring axiom states that R is a monoid under multiplication. So this structure here are equipped with the second binary operator is a monoid. In a quick recap, or quick recap of what monoids are, is that what monoids satisfy is that for all A, B, and C inside our given monoid, say M or mu, A times B plus C is equal to A times B times, sorry, this is times, sorry. A times B times C. Okay, that's the first one. And of course, it's a monoid. A monoid must contain a multiplicative inverse. So there exists some E, not one, some E, such that for all A inside the monoid, A times E is equal to E times A is equal to just A. So we have a multiplicative inverse for our monoid. Assuming that our operation here is multiplication or addition, it could be addition, or equipped with this could be an abelian group and a monoid with our multiplicative inverse our additive inverse being 0, or a neutral element being 0, because add any number to 0 and we just get that number. Okay, so it satisfies these two things. So 1, our ring is an abelian group, and then 2, our ring is a monoid under multiplication. So it satisfies these two properties. And then the third axiom is that multiplication is distributed with respect to addition. So this operation, our second one, is distributive with respect to plus. So what I'm saying is, given some inputs A, B, and C, A times B plus C is equal to A times B plus A times C. So we can distribute numbers here. And so likewise, B plus C times A is equal to AB plus AC. It's pretty much the same thing. Or BA, sorry, BA. It's the opposite. BA CA. We need to specify that these two are not exactly the same, because we can construct, or it's possible for us to construct some ring such that these two properties are different. So we must state them independently. So now, what's an example of a ring? An example of a ring, I suppose, is the integers, z. Equipped with addition and the multiplication operation. Because notice that for all the integers, it satisfies the first axiom. So let's discuss about the first axiom first, or the first ring axiom. Notice how any inputs in z, which is the integers, let's say 1 and 2. I know I always use 1 and 2. It's the most simplest example. I could pick up an arbitrarily large number, an arbitrarily small number, and it would just give me the same, satisfaction when it comes to talking about it being a ring. So it is an abelian group, because notice, if we add 1 and 2, it would give us the same input that's adding 2 and 1. So 1 plus 2 is still 3, and then 2 plus 1 is still 3, no matter what you say, right? And next, multiplication, or integers equipped with multiplication, is a monoid. Because notice, if we have 3 inputs, say 1, 2, and 3, A, 1 times 2 times 3 is the same as 1 times 2 times 3. So it's confirmed that 1 times 2 times 3, 2 times 3 is 6, and then 1 times this is just 6. 1 times 2 is just 2, times 3 is 6. Same thing. So that satisfies this property now, that it's a monoid. And the third condition is that it is distributive with the plus. So notice, okay, let's do this thing. So it satisfies these two things over here, okay? So a times b plus c is equal to a times b plus a plus c. So again, let's use 1, 2, and 3. So 1 times 2 plus 3, that's still 5. And then 1 times 2 is 1. And then 1 times 3 is 3. And so 2 plus 3 is 5. So it gives us the same input. So that means it is distributive. So now we can say, after me explaining how integers are essentially a ring, we can say that this construction over here is a ring. Now I can also explain that the set of all n by n matrices equipped with these two operations is also a ring. In fact, rings are most well known to be sort of generalizations for linear transforms and matrices, but that's for another footnote. So that's the gist of what a ring is. And so now, what we want to do is apply what we know about rings now and talk about modules. So now, okay, let's apply this to our theory and assume that R, our underlying set, or our bar, is some set of femboys. If we can combine two femboys together, say, let's use O cross P. It's possible. This O cross P could definitely be a ring. Because notice how we can break down femboys. According to, well, our second theorem of position theory, we can break up femboys into multiple linear combinations of other femboys. So that means we can already break down, or we can show that a femboy can be broken down into some principal linear combinations of these guys, showing that indeed our femboy set is an abelian group under addition. And now to prove, or to show that our femboy ring, or F ring, is a monoid, we just simply need to show that it satisfies these things. So we have an identity femboy, such that if we multiply every femboy with respect to the identity femboy, we would get that regular femboy that we have. And that's pretty trivial to say. We can just state it. If we are using O cross P and describing femboys in terms of position states, we can just say that our multiplicative inverse, or identity rather, is just 1. Or our multiplicative femboy is just 1. And for this one here, we can just try to find 3 position states and then show that their multiplication, or just rather the sort of the multiplicative resultant of these guys, are the same if we put some parentheses in between 2 of them, or either 2 pairs of the given femboys, right? So yeah, we can construct an F ring so long as it satisfies these 3 axioms. So that's a new thing that we've added to our course, or to our theory. An F ring. So, okay, now that we've discussed about rings, and after you guys have digested, so I suggest you guys pause and digest the information, let's discuss about modules now. Let's discuss about modules. And also how it would probably O cross P. So, note that O and P can form rings. O cross P could also form a ring already. Because so long as we have the operation, well, dot, solid dot, that maps O cross P onto either O cross O or P, we have ourselves already, and then so. Also, this plus that maps O cross P onto O or P. We already have ourselves a ring here. So O cross P, I could put these 2 operations, would form a ring. So long as you define O and P such that it satisfies the ring axioms. Okay, so now let's talk about modules. said a while ago, a module is a generalization of a vector space. So you guys know about our Femboy vector space, right? Now, what we want to ask, or let's take it a step further and say, what element is our Femboy vector space, or what set or structure is our Femboy vector space a part of? Like how when we ask, given a P space, what is the next step, or what is the next level in the hierarchy which our P space is part of, right? So that's the P category, and it's part of the paper. I haven't discussed it in position theory yet because it wasn't relevant. But in my paper, you will notice that we took it a step further. That's indeed the latest entry in my theory. And then we're saying now that, well, given a person space, we want to ask what they're a part of, what they're subsets of, or what they're elements of. And what their elements or subsets of is a person space. So now, what we want to ask is, what is a Femboy vector space or a Bussy space part of? And that is what we call the Femboy module or F module. So to understand what an F module is, we must first talk about left and right R modules, or just modules in general. So in pure mathematics, a module is not indeed what gives people or students during the pandemic misery, but is a mathematical structure. Okay, that is a ring. Is a ring R with a multiplicative identity. Okay. With a left, okay, so let me rephrase this definition. Okay, so let R be a ring. So our next definition, let R be a ring. With some multiplicative inverse. You guys know that it should have an inverse, right? A left R module on M consists of an abelian group, M and plus, and an operation, such that for all Rs in R and XY in M. Yeah, okay. A left R module M, okay. So there are two types of modules, a left and a right module, a left R module. So this is what I need to discuss first, what an F ring is, or Femboy ring is, because when we talk about F modules or Femboy modules, we need the definition of a ring. You guys need to know what a ring is, okay? Because we need that in defining what a module is. So I'll call a left R module Rm. So we say left, or we use this notation because it's on the left. It's the left R module of, well, our given abelian group M consists of an abelian group. An abelian group, which is M, then plus operation, and then operation, I will go plus, that maps R cross M onto M. Such that, so here's where things get a little bungee. So I'm going to need you guys to bear with me here. Such that for all Rs in R, so two elements elements inside our ring, and 2, and for any 2 pairs of members of M are abelian group, this left R module satisfies these 3 axioms. The first axiom is that multiplication is distributive with respect to addition. So R times X plus Y is equal to R times X plus R times Y. Rx plus Ry. The second axiom is that R plus X is basically the same thing, but this time we're multiplying R and or we're adding R plus S. Yeah. So R plus S times X is equal to Rx plus Sx. And then the third axiom is that okay, so we're now stating about shorthands here, so you guys know that, well, multiplication, or this dot here denotes multiplication. Now we're just saying, basically, this is just the same as Rs here. So it's just a restating of this, but in a shorthand way. So Rs multiplied by X is the same as R times S times X. So what we're saying now is that we can shift this parenthesis here and it would still give the same output. And then the last one is the simplest one. So our I, or our multiplicative identity times any number X is just X. So our multiplicative identity here in our ring R multiplied by any member of M would give us just that member. So 3 times 8. Suppose our multiplicative inverse, or suppose our ring is the integers equipped with the plus and the multiplication operation, and suppose M here is also the integers but equipped with just the addition operation. We know that 4, the number 4, or the integer 4, is a part of both of these guys. And we know that our multiplicative inverse for our ring is 1. So our multiplicative inverse times a member here, so 4, times 1 is just 4. So as stated here, our multiplicative inverse times any number or member of this, this abelian group would give us just that number. So very trivial property of it. So now we call this operation scalar multiplication. So this would sound familiar with you guys because it takes 2 scalars from here. So it takes probably a matrix. You can think of, well, R here, our ring here could be a ring of matrices, right? And then now we have some scalar over here because this M is just 1 dimension. So it only has 1-dimensional quantities in it, just numbers, or constants, or let's call them in physics, scalars. When we multiply, or when we take the input or multiply a matrix with a scalar, we just get some, I suppose, matrix or scalar. Mostly matrix though. So that's what? That's why it's called scalar multiplication. So this is a generalization of our intuitive notion in physics that we can multiply some linear transformation or some switch of system and vectors. Multiplying vector, or could be also a ring of vectors, and then we could think of this as some scaling of a vector, right? By some by some scalar quantity. Okay. So now we've discussed a left R module, a right R module is just the same thing here, but instead we're swapping these two. The thing about multiplication in abstract algebra is that they're not necessarily commutative. This here is not necessarily the same, so R cross M is not necessarily the same as M cross R. Because by definition, A Cartesian product, that's a Cartesian product over there, of two sets A cross B is equal to the set of all pairs A, B, such that these two, A is from A, big A, and small b is from big B. And if we swap this and say B cross A, our ordered pair here would swap. So notice that if we describe A by our x-axis and B as our by our y-axis, swapping the two coordinates would give us a different point in space. So that's why this Cartesian product is not commutative, not necessarily commutative. And that's why we have left and R and right R modules on M. So the denotation of a right R module is just, basically we're just going to move this R to the right of the M. And this time, it's now an abelian group, N and plus, same thing, but this time our operation takes two inputs, that is M cross X. So this time, right R modules takes two inputs, which is just M cross R. M cross R. And then just maps it onto just M. Same thing, but we just swapped it. And then so we have a different pair now. Different kind of point. So that is on left and an R module. So now that we've considered the case wherein the Cartesian product is not the same, when we consider that the Cartesian product of these two M of the ring and this abelian group are the same, so if we say that the R, the right R module and the left R module of M, if the left and right R modules over M are the same, then we just say that it's just a regular module over M. Just a regular module. So now, how does this apply to our theory? Now, notice how if we have some F ring, we can construct some and some abelian group, any abelian group, honestly, then we can construct some right and left F module, morning miss. So we can just construct some F module such that, well, the cross here would be the same. And yeah, very simple. We just need to have an F ring, and then we need an abelian group consisting of some underlying subset of our universal Femboy group. And then we got ourselves a left F module, or right F module. And assuming that the F modules are the same, the left and the right F modules are the same, we just have a regular F module. So that's considering modules. And yeah, that's it for this footnote. So really good idea that Rulu suggested this to me, because I really glossed over these things, to be honest. I glossed over modules and rings. I should have discussed them. I did discuss about magmas and groups, but and also abelian groups, but I didn't consider modules in the first place. So great way of sort of generalizing our theory, our position theory lectures, and O cross P, of course. So that's pretty much it for this lecture, or this this footnote. So I'll be adding more footnotes if I get more discoveries or more insights, I believe, and I'll state that to you guys. So an important thing to take away from this this footnote is that it is not necessarily commutative.